Hey, all right, everybody. So it is week 7. Yeah, we're just about to turn the halfway mark here in fall semester 2016, and we're going to move on to topic 7, liquefied petroleum gas. Before I do that, though, I'm just going to catch up on previous week's discussion boards. Let's just take a look here, week 6. You know what? I'm gonna actually kick that off. So I didn't post anything last week. So. So that's my submission for last week. Gary's limping in as we speak, so looks like your horse got the better of you there.
My freaking laundry basket.
Oof, that's rough. That's rough.
I was walking by it. I don't know, you know how they got the little weaves in it?
Jumped out and grabbed you,
My
huh?
pinky toe caught in one of the little holes in the weaves.
Oh boy,
Bent sideways.
that sounds fun.
Is that you?
So let's take a look at the week 7 reading assignment. So it's chapter 7. And I'll just take a peek at that myself here.
LPN?
LPG, liquefied petroleum gas. Yeah. So anyway, I'm just going to read a little blurb or two here. It just says, liquefied petroleum gas, LPG, is a mixture of propane, which is CH3, and butane, CH4. So, living in Montana, you see a lot of propane, a lot of propane tanks out outside of houses. And again, propane is CH3, so a little heavier than methane, obviously heavier than ethane as well. Butane heavier still, and that's typically what we see in lighters. So LPG is a popular fuel for internal combustion engines. This popularity comes from many features of the fuel, such as its high octane number for spark-ignited engines comparable to gasoline, heating value that ensures similar power output. Other features include the possibility of transport and storage in the liquid state because of the relatively low pressure of saturated vapor in normal temperature range, better exhaust gas composition, and lower cost per energy when compared with gasoline. So that's a good question. You know, why don't we use LPG instead of gasoline if it's got lower cost per unit energy? The last feature is a reason of rapidly growing popularity of gas fuel in the world. The above-mentioned features of LPG also give the possibility to applying this fuel to compression ignition engines with relatively low compression rating. So the idea is you don't have to squish it as hard before it ignites the LPG. Okay, the possibility to obtain the same power output from the engine fuel with diesel, oil, and LPG. Also, the high octane number allows compressing of the propane butane with air in engines with low compression ratios without apprehension of self-ignition. So self-ignition is what happens in a diesel engine. You squish it and it just hits the critical temperature. This, in addition to improved exhaust gas competition, makes it very attractive. All right, so the table 7.1 talks about what the ratios look like. So the U.S. is not mentioned. We just don't see LPG as a transportation fuel. So France, Austria, Italy, Spain, Sweden, UK, Germany, Australia. In the UK, it's 100% propane. The country with the highest butane rating is Italy. Relative CO2 per kilojoule, LPG is better than gasoline as well as diesel. The lower heating value, if we just look at on a per kilogram basis, it's actually higher at 46.1. If we look at it on a liters basis, it's the lowest. So it just means you need a bigger tank. On a per mass basis, the LPG is better on a per mass basis, on a kilograms per unit mass.
So it's kind of like dimethyl ether where it has to have a bigger tank, or?
The same amount of energy, yeah, it's just because it's less dense, that's the only reason, but not substantially. It's
Not for the reasons that dimethyl ether has to have a bigger tank for the pressure. Isn't that why it has to have a bigger tank? It's something to do with the pressure, you got pressurize it for some reason? Or else it'll decompose?
Well, yeah, this does have to be at pressure, otherwise it will evaporate. You know, it's the same reason your butane lighter and your propane tank out back, yeah, they're under pressure to keep them liquefied. Yeah, same physics going on there. All right. Well, from here, I'm not going to mess around with the book much more. I'm just going to read through Kern's notes. This is relatively. So we've dug into the chapter a little bit, 203 to 226, relatively short chapter. Here are the notes. Liquid petroleum gas, there it is. Okay, so another thing to note, and I was looking at this earlier with my 101 students, when a petroleum well is tapped and you're going after liquid fuel, there's typically gaseous fuel along with it. And so natural gas, as it is produced at the wellhead, there's some cases where there's just not the technology in place to capture the natural gas. It's just flared, right? So primarily methane, but also ethane, which is C2H6, propane, C3H8, butane, which is C4H10, pentanes, et cetera, et cetera. The general formula for this, if you just do a little bit of simple, if we do this, so here's methane, 2 carbons is ethane, 3 carbons is propane, 4 carbons is butane. And then if we know that this has 4 hydrogens, 6 hydrogens, 8 hydrogens, and then 10 hydrogens. So what's the formula for this thing? It's basically CnH2n plus 2. If that makes sense. So let's just try it out. For methane, if n equals 1, we have C1H, 2 times 1 is 2, plus 2 is 4. For ethane, if we have N equals 2, C equals 2, 2 times 2 is 4, plus 2 is 6. If N equals 3, we have C3H, 3 times 2 is 6, plus 2 is 8. And then finally, for C4H10, because 4 times 2 is 8, plus 2 is 10. And then, of course, you could go ahead and draw these out. And in every case, you have saturated bonds. There's ethane. I'm not going to draw all the hydrogens in, but you can sort of count them. Each line is a hydrogen, and then butane, just on up the scale. So if you see this formula, it's basically these simple hydrocarbons, starting with the simplest, methane. So as stated, this is a question just asked here in class, is why are these pressurized? Well, the reason is that they are gaseous. They're gases at normal pressures, but under slight pressure, they will liquefy. The fact that they become hazardous makes them that they can become liquids makes them hazardous. Well, it's just a fire hazard. That's all it means. It's also a breathing hazard. If you breathe these things in, it'll kill you. And there's your explosion possibility. So in some relatively informal language, in the early oil field days, natural gas was something of a pain in the butt, and it would just be flared. Obviously a huge waste. You still see some of that, and you'll see these small flares at some refineries, and you might say, oh, why are they burning that? It's such a tiny amount. I'm not justifying the burning, but you could think of it in a similar way to your pilot light. It's just like an old school pilot light. And I think it's also a way for the distillers to know that there's pressure in there. Like if it goes out, then something's wrong. There's a buildup somewhere else. It's just, okay, or the same way of leaving your winter cabin water running through the winter so the pipes don't freeze. It's flowing, it's flaring, it's not backed up.
Plus CH4 is twice the heat trapping gas as CO2. Right,
and the other thing is it's sort of better in general to turn that methane into carbon dioxide from a climate change perspective. Yeah, that's a good point. Yeah. So in a lot of ways, this methane is just kind of a waste. It's a waste gas that's sent off to cook with, heat water with. The fractionation plant, and that's basically where you're just sort of cooking these various mixtures off. The light stuff goes up, the heavy stuff stays down. Okay, the text mentions that 3 to 40% of a barrel of crude oil could be converted. So there are these smaller molecules inside a barrel of crude, and in fact that's where a lot of this comes from, but it tends to just stay blended as part of that crude oil on its way to the refinery. Okay, as we said, mostly propane. Here's a butane. So you still have 4 carbons, but it's just a different type. So the straight guys are called alkanes. The different configurations are isoalkanes. In the case of this butane, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. If I did that right. No, there's 10. 3 plus 1. So going back to the notes, butane, you still have, let's see, 8, 10. Yeah, you still have 10 hydrogens. It's just that one of the carbons, instead of having a double hydrogen, it's got 3 carbon bonds with it, a single hydrogen, and then the other 3 each have 3 hydrogens. We already looked a little bit at table 7.1, so Turkey, South Korea, Poland, Italy, and Australia are all using them. Higher ignition temperature, that's kind of interesting. So it's safer than handling. You can get hotter and not spontaneously combust.
Like mustard gas.
Well, yeah. Yeah, so it is heavier than air, and it could sit along the ground and sort of pool prior to ignition. Oh, this is true too. If the gases come out, it can be cold enough that it could actually give you a cold burn.
Well, spark ignition, that's basically what it is, isn't it?
Well, spark ignition.
Yeah.
Well, it's spark ignition where you spark it with a spark plug versus compression, which is more of a diesel.
Just heating the cylinder and using the pressure to.
Ignite it, yeah.
Oh gosh.
So we already mentioned larger onboard storage tanks. Lower energy density, so you can't go as far unless you have a larger engine.
Wouldn't adding water also add oxygen to the process?
Adding water is,
Well, it says, yeah, adding water, you get better fuel efficiency on that last page was, here's,
I'm sorry, I didn't catch that.
it looks like engine efficiency increases with increasing water content. I'm guessing the addition of water better cools the cylinder, which allows fuel gas to enter thereby increasing efficiency.
That's
It's a puzzle to play with for a bit, huh?
yeah, let's take a look. 7.4. That's a new one. That is not a test I have any direct experience with, I'll be honest. 7.4, let's dig into it a little bit. No, I mean, that's strange that you would add, because water is one of the combustion products. I'm not sure why you would add a combustion product to your fuel in order to increase efficiency. Okay, so I'm just looking at figure 7.4 on page 213. Brake thermal efficiency variations. And the ranges are going between 26 and 38%. And the engine speeds are between 1,000 and 4,500 RPMs, with engine speed for various water fuel mass ratio. Of water injection.
Well, it seems like there's a sweet spot here.
Well, yeah, but it looks as if, well, you know what? This is a little strange. I mean, I'll just show the figure since we're talking about it. This really does not look like any engineering chart I've seen before. So the highest efficiency has 50% water in it. So why wouldn't I go up even higher and get even higher efficiency?
Well, I think it goes to a sweet spot, and then it drops.
Well,
It's not like a,
where's the sweet spot? What happens when I go to 60? I mean, any other engineering chart, this seems,
see, I'm not fully comprehending the break thermal efficiency. I'm more looking at the integral beneath the curve here.
yeah, well,
Volume.
what I interpret the brake thermal efficiency would be if the engine's just running under a braking load.
Okay.
And they're looking to see how much heat is being generated on that brake. And now that just LPG only, it is the lowest. This is the lowest efficiency overall. And as we get greater, so you know, from an eighth to a quarter to a third up to 50%, at some point, oh, let's just put water in and burn. So this is not a well done graph. The sweet spot would show, you know, if in fact.
3,000 RPMs.
Well, but how about as a function? How about sweet spot as a function of water content? Where's the sweet spot?
It's right on top.
It's right on top. Well, then it's not a sweet spot because they didn't go all the way up to 100%. But, you know, a proper graph would show it coming back down. So when you got to 0.66, it came back down to where your 0.33 was. When you got to 90%, it would come back down to where your 0.125 was.
So they didn't do a full fleshing.
Yeah.
I like how they use the R program to make this
Well.
diagram. But you can tell by the X's and the O's.
Now, what could be happening, and it doesn't say, you have to go read the paper. Where is the water going into the fuel, or is it a water cooled engine? It doesn't say where the water's going. Effective water addition.
Water fuel ratio, isn't it? Because you got the mass of the water on top of the mass of the fuel would be a ratio, wouldn't it? Water over fuel.
Oh, it's just not clear.
Okay, I'll take your.
It's just not clear.
Because I'm working out too much on this.
No, because you're putting. You'd be putting water into the fuel and saturating it with. You'd be saturating it with oxygen.
Which would give you a better combustion, you would think, because the more oxygen in the chamber you could push in there, the more combustion you're going to get towards completion.
Well,
that's what I would.
So let's just take it to the extreme and say let's just put pure water in there and burn water with oxygen. It just doesn't hold. Or we would just have water. We would just all be putting water in our engines and
Well, if somebody could make water burn, they'd be in there. Without having to slick oil over the top of it. Maybe it is. Maybe it does decrease the thermal breakdown in the chamber, so that, like he's saying here, so that it allows, instead of evaporating in the heat when it comes in and instantly converting, it's coming in and not evaporating until the combustion occurs. Maybe that's a pre-ignition thing.
it's a strange one. I got to admit, like the graphs do not play out as if they actually went through this full experiment. They really don't. Because at some point, like you were suggesting, you would hit a sweet spot and then you would come down from that sweet spot when you got to, say, pure water. It's interesting to consider, though.
I mean, if you look at
It's tough to deny it, though. I mean, it's right here in the book. How unless it's just some kind of fraud.
Yeah, they
Let's get it going on the discussion board and let's see if we can get Kearns to weigh in. And someone should go find that paper too. I'd love to take a look.
It's Oscan H and Solomez. That one?
Yep, Oscan and Swillamez. Energy Conversion and Management, 2006.
Well, we're using the average Linreg line on that anyways. Linear.
What's that?
Well, they're scatter plot because they're not really on the curve.
Well, they did some kind of curve fitting to it.
Linreg, yeah. It's just how I do it on the calculator, that's how I quote it. So.
No, that's a good one. That's a new one.
Yeah, I seen that. That's what I was reading. I was like, put more water in it, it gives it more efficiency.
No. Well,
Because that's just, I mean, that's just gonna add to pretty much the water coming out the tailpipe, wouldn't it?
I mean, we could do a little, we could just do a little stoichiometry here.
Geometry, I love that word.
We like stoichiometry.
Stoic.
Well, so let's say we've got,
Gallery speaks.
stoic. Let's see, we got this. Here's propane. We'll put butane in there. And then, if we just burnt these two guys, we'd have to dive, pretty far into the thermodynamics here to get at this, but we just at least did the stoichiometry. And we started adding oxygen. Let's just figure out. So we've got carbon coming out. We've got 7 carbons, and the only products we're going to get. Let's assume complete combustion, and that's CO2 plus H2O. So just simply, we'll throw a 7 at that. And how many hydrogens do we have? Oops, sorry, 7. Throw a 7 at that. And then how many hydrogens? We've got 6, 8 plus 10, 18, so there's a 9 there. So there's 14 plus 9, 23. So we've got 11.5 of these guys going in to get that much CO2 and H2 coming out. So let's just try it by throwing some water in instead. So if you got this, so the question is this actually thermodynamically more efficient or not? We've got H. So again, we're going to have, so the only carbon source is from the propane and the butane, so there's CO2. So again, we'll have 7 of those guys, plus H2O. Now, how many hydrogens do we have? So if it was 8%, let's see, what's the molecular weight on this guy? 12, 24, 36, 36 plus 8 is 44. And this is 12, 48 plus 10, 58. And what did they say? What was one of the mass ratios? 50% water by mass?
Well, yes.
So that's 16, this is 18. So what's 44 plus 58 is There's a 2, there's a 1, 102. So let's just say we had 5 waters going in. That's a 50%. That's a 50%. So we have 5 of these guys. Okay, so how many H2s do we need? We had 8 there, 18, plus another 10, 28. 28, 14.
Yeah. Well,
So-
it's gonna add more oxygen there
So,
too.
yeah.
Because you're gonna
Let's see if we got enough. If we got
5 more oxygen.
how much oxygen though? So hang on. So we had 5 oxygens there already. Well, how many do we need on the right hand side? We need 14 plus 14. We need 28. We got 5 coming in, so we need 23 more. 11.5. That doesn't seem right. That's kind of
Yeah, I don't see where.
like it's just the it's like the same number of oxygens coming in.
It's going out. Yeah.
Well, there's no oxygen coming out.
Oh.
There's no sorry, oxygen is coming out, but diatomic oxygen is only going in and not coming out. So let's just double check. So we started out. This has a molecular weight of 44, 58. That's 102. Water has a molecular weight of 18, so we need 5 of them to get up to a 50-50 weight. There's 7 carbons, so that, and then there are there's seven carbons, and how many hydrogens went in? Well, there were 8 there, plus 10 there, it's 18. Another 10 there gives 28, so there's your 28 hydrogens. And then the oxygen's coming out. 14 there, 28 there, total. 5 of the 28 are here, so either 23 are right here, either 23 oxygens. So it's the same.
Yeah, it's a difficult. I think you're gonna have to use instead of a full unit on that, you're gonna have to have 7.5 at somebody that has to.
Well, you could just double it to get to that, but
I always want to simplify things instead of having it.
no, it would in some ways be easier, but well, yeah. So I guess the question is, are these if you are adding water to the fuel, are these waters just are 5 of them simply passing through? Gosh, I got to pause that for 1 second. This is kind of strange. I hadn't thought about it. Well, this kind of remains a mystery whether these extra waters are part of the combustion. Is one of these oxygens from the water coming over the CO2, and are the hydrogens from the water? Well, the only place for them to go are back to another the H2O. I don't know if there's a hydrogen gas intermediate in there or not. That's a good one. Worth looking at, checking out. It's a good puzzler. But again, it's just kind of strange that they just stopped at 50% water and didn't look for an actual optimum in their testing.
I mean, It's like throwing water on a fire. You can throw a little bit of water on a fire. I mean, it'll make it smoke. It might douse it a little bit and keep going, but you throw a whole bunch of water on a fire, it's gonna douse it out pretty good. Maybe
Yeah.
they get past 50% and it just doesn't work anymore.
Yeah, I just see the water as an energy absorber, not an energy creator, not a combustion source. Okay, conversions, so world demand, this is millions of metric tons. It's on the rise. North America is mentioned there in the blue. There's Asia in yellow, and it seems to be pretty steady worldwide, not dominated by any particular place. One thing to note is the gas is invisible. Can't see it, can't smell it.
Isn't it odorless? I'm just gonna add
Yep, no smell either.
a skunk smell to that.
Yep.
So it smells skunky. So you know that it's leaking. So you might
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure.
Wow.
As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing the greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion.
Not to mention solids.
The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fire and other damage. It all happens quickly, with little warning.
Didn't hit anybody though, right?
No, it went out into the woods, and luckily it didn't start the woods on fire because it hit out in like a marsh, so it went down.
All right, so that's the chapter. These are all mentioned in the book there too. All right. Well, let's just take a look at the example problem. Oh, this is a good one. Okay, and I'll just give you remind you what interpolation versus extrapolation is. If we have a set of data points that are here, here, and here. Anything that happens in this range. So for example, if you want to know what's going on at this point, this is interpolation. And if you want to know what's going on either at this end, this is extrapolation, and then same thing here. So anything that happens within known data, again, is interpolation. Anything happening outside of known data is extrapolation.
Find the equation of the line and extrapolate it.
Yeah. Okay, let's say that we need to estimate ignition delay data points for each of the 4 fuel combination shown in an equivalence ratio of 0.2. So here's full diesel fuel. Here's 10%. The diamonds are 20%, and the circles are 30%. You can see from the graph the data begin at 0.3, or essentially the 30%. But a reasonable assumption would be to extend the data lines leftward to intersect the y-axis. So what's going to happen when you get all the way?
We're already sitting on the x-axis there. 0.2. See that?
Yeah, so we're trying to figure out what the equivalence ratio would be at 0.2 for each of these. There are 2 ways to do this. One is to draw the best straight line, so that the question is where, in each one of these red lines is sort of a straight line. You can kind of look at that and say, oh, is it really tangent here or not? Or the second one would be to curve it somehow. Well, it seems apparent that the data are not linear. Well, they're not, because they have this curve to them. They are curves. It still seems reasonable to draw a straight line estimate, which is what I have done in the scan below. From this drawing, I would estimate that the following values for ignition delay at a ratio of 0.2 are, so propane plus 10%, those are the triangles, and you can see it comes in just below 3.5, so he calls that 3.1 milliseconds. 20%, just above 3, so 3.1. Propane, 2.3, and then diesel fuel, 1.7. And again, this is just kind of eyeballing, and unless you have some kind of equation for this thing or data, there's a fair amount of uncertainty in terms of exactly.
That's exponential, isn't it?
No, I'm not going to say these are exponential. I'm not going to say that it's some kind of least squares fit, but the function, it's anybody's guess. I mean, the one thing that makes this a little suspect is that these 2 lines tend to cross out here. And the other thing that makes it quite suspect, there are no error bars on any of these dots. Like if this, and I don't know, I didn't do the experiment, but if you were to do this experiment, you would repeat every one of these data points 5, 10, or 20 times and have error bars on them, which would presumably bring them into some type of, actual function. Because this, just even seeing that big belly in that curve right there versus that one makes this suspect. So I wouldn't say this is the most scientific study, but at least it gives you some kind of ballpark. I think that's all he's doing there.
So what does he want us?
Well, let's take a look at the homework.
Well, that's the example.
That's the example problem. Using figure 711 for propane. Figure 711 on page 218. For a percentage of 90%. So in this case, what he's Guys, let me show you. I'll show you something here. Let me do it. We'll do it this way. Let's do it this way. Here's the formula for doing. This is actually just called the Newton-Raphson method. So here's what I'd like you to do on this chart. So he's asking, you're out here at 0.9, and there's a couple numbers here. I'm not going to use the exact numbers. I don't want to give away the answer. But let's just say this is 0.25, and I'm going to intentionally use a different number. I'm going to say this is 0.24, or sorry, no, let's do 0.35.
Change everything out of money.
And let's just say we want to know the number at 0.31. In fact, I'll give you a slightly more challenging problem and let you simplify it for the homework. Okay, and what we'd like to know, and we'll just do it linearly. And let's let this point right here be 0.85. So let's just say we have this point right here, which is 0.8, comma 0.35. And let's say we have this point right here, which is 0.9, comma 0.25. And we have another point right here, which is 0.85, comma y. And we'd like to know what y is. And we're just going to use just something called the Newton-Raphson method. So if this is x and this is y, all we're trying to do is figure out what this y is right here. So quickest way to do it is to say that we know the we're going to draw a straight line through it just for the sake of speed, efficiency. And we know that this whatever point we find right here is going to be on that line. So we know that the slopes, so if m is the slope of this line, it's also going to be the slope of that line. The slopes are going to be the same. So what we know is that the rise over the run is going to be the same. So the rise is going to be 0.25 minus 0.35 over 0.9 minus 0.8 equals, and now you can choose either one, but I'll just say y minus 0.35 over 0.85 minus 0.8. Okay, so just to review what I did, this first line, I'll just call this line number 1. It's this guy right here. And the second line is number 2. And all I did was assume, well, I didn't assume it, I know that the slopes are the same because this point that we're looking for right here sits on that line. So the slope's the same. So these are the 2 points I know. Starting off with these 2 points I know on either end, and I'm just looking for this value. This is y right here. Newton-Raphson method. Okay, so from there, I can just solve it. Equals 0.1, that's a negative 0.1. 9 minus 0.8 is 1.0 equals y minus 0.35 over 0.05. Now I'll cross multiply, and I've got negative 0.005 equals y minus 0.35. Let's see if I've made any mistakes here or not. Let's see what I'm doing. .25 minus 0.35 is negative 1.0. 0.9 minus 0.8 is 1.0. Y minus, let me just pause it for one quick sec. Okay, I see where I made my error. For some reason, when I subtracted 0.8 from 0.9, I got 1, but it's actually 0.1. So now we'll cross multiply, and we have negative 0.005 equals 0.1 y minus 0.035. And now let's just multiply everything by 10. Let's multiply the whole equation by 10. So negative 0.05 equals y minus 0.35. Yeah, this is the answer we, of course, suspected. It's just that y equals 0.3. Perfect. Okay, so I just caught my error. It was that. So just to review what we did, use the Newton-Raphson method to find the y value of this unknown point. And so we said we were going to start off with this top point here, which is 0.8, 0.35. We know this other value down here, which is 0.9, 0.25. And we know we're looking for a value midway between the two on the x-axis. And what we're looking for is this y value. So in order to do so, we know that the two lines are, in fact, collinear. That midpoint is on there. We set the two slopes. It's just, slope is just rise over run. So we subtracted the rightmost point from the leftmost point. So there's your rise on the top, here's your run on the bottom, and said that equals the rise over the run of line 2, which is that just top half, if you will, of the interpolation line, and came up with a little bit of algebra that the value is 0.30. So that's interpolation, plain and simple. And so what the problem itself is asking for So for a propane percentage of 90%, determine the fuel conversion efficiency for 35% load. And that's on page 218.
Which would have to be between 20 and 25. Because your load at 50% is,
Well, it's going to be, yeah, I'm just looking at the figure here. The fuel efficiency at 0.9 for 25% load is 15. And the fuel efficiency of a 50% load is 23 or so. So it's going to be between 15 and 23. Yeah.
the other side of the load.
Yeah. All right. That's a wrap.